Today we're going to talk about the difference between linear and nonlinear differential equations. On this slide, I presented the main existence and uniqueness theorem for first-order linear differential equations. A similar theorem we'll see exists for higher-order linear differential equations. So what does the theorem say? Well, if we take a first-order linear differential equation and put it in the standard form, like this, y prime plus p of t times y equals g of t. The theorem tells us the following. If the functions p and g, our coefficient functions, are continuous on some open interval, in this case the interval from alpha to beta, the same thing would apply if we have the whole real line or an open ray, say the ray from alpha to infinity or minus infinity to beta. Everything works the same. So if you have continuous coefficient functions on some open interval I, and we have an initial condition that takes place at t naught, some point in our open interval I, then the theorem says there exists a unique solution, y equals phi of t, that satisfies both the differential equation and our initial condition, y of t naught equals y naught. Y naught here is just some arbitrary initial value. What does this mean? Well, say we want to solve this initial value problem. And we have an initial condition here, which is the point t naught, y naught. Here, this is the t-axis, not the x-axis, the way we're writing things. Here's our initial condition, says that our solution has to go through that point. If, say, p and g are continuous on some open interval I, and let's say I draw the open interval I like this. I'm just going to draw an interval along the x-axis. It could be a larger interval, but let's say we know that that open interval I includes the point t naught. Here t naught looks like it's approximately 4. Then our existence and uniqueness theorem says not only is there a solution to this initial value problem, that means a solution to this differential equation that satisfies our initial condition, but that solution has to be valid on this entire interval. Who knows what it looks like? It might look something like that. But we know there'll be a solution that has a domain that includes this entire interval I. If we have a differential equation, even a first-order differential equation, which is not necessarily linear, then things are very different. We still have, which is a very good thing, some sort of existence and uniqueness theorem, but it's a much weaker theorem. So here I've stated the theorem. The theorem applies to a first-order differential equation written in this standard form, or an initial value problem in this standard form. We have y prime is some function of t and y. The theorem says let the functions f, that's this function f, and df dy, the partial of f with respect to y, be continuous in some rectangle. And this means a rectangle in the ty plane. And the rectangle should contain that point t naught, y naught, where our initial condition takes place. Then in some interval centered at t naught, this interval is just an interval of radius h centered at t naught. It's the open interval from t naught minus h to t naught plus h. In some interval contained in this interval from alpha to beta, there has to be a unique solution of the initial value problem. What this theorem doesn't tell us is how big h is, how big this interval on which our solution exists must be. It could be very small, even if our functions here, our function f, is continuous for all values of t. What does this mean? Well, let's say we have the differential equation y prime is f of t and y of t naught equals y naught. Again, let me just pick a different location, but let's say here's our point, this is our t-axis, here's our point t naught, y naught. And so we ask where are both f and df dy continuous? Well, remember, f and df dy are both functions of two variables, t and y, and we have to compute df dy, and we have to ask where both of them are continuous. And if we're lucky enough that they're both continuous in some rectangle that contains the point t naught, y naught, then what does our theorem tell us? Our theorem tells us that there actually has to be a unique solution to this differential equation that, along with our initial condition, in other words, a solution to this initial value problem, that goes through this point, but that solution has to exist on at least some small interval centered about t naught. The solution might exist and be unique on some tiny interval. Here, that interval could look like here from t naught minus h to t naught plus h. And h could be very small. Now, if we're lucky, the solution might exist over a much larger interval, but our general existence and uniqueness theorem can only guarantee us some small interval on which the solution is guaranteed to exist.